So our speaker is Anja-Verena, and she's a PhD student in the NIG lab. And broadly speaking, her research is all about understanding lower extremity movements and how those are influenced by both muscles as well as external factors. Today she's going to talk about a segment of that work, the foot segment specifically, I think, from what's up there. And when I looked at her CV, I saw that kind of her background very much lines up with this type of work and prepared her for doing this type of research. So let's talk about that a little bit. For her undergraduate degree, Anja got a Bachelor of Science from the German Sport University Cologne, which specializes with a specialization in coaching and exercise physiology. After that, she did her master's degree, also in Germany, at the Otto von Guericke University, where she studied the biomechanics of foot movement. And I noticed that Dr. Ben was her co-supervisor there. So I bet that's where kind of that connection was made that brought her as a PhD student here at the HPL now. I think that continuity really did her a lot of good, because Anja was able to publish 3 papers in the first year of her PhD, which is a really impressive thing, especially when you're starting out. But it also explains her choice of future plans, which she says it's really just to stay sane throughout the rest of her PhD. So good luck with that.
Thank you.
How's it going so far?
So-so.
So-so. So before I hand it off, just want to end with a couple of fun facts about Anja. I used to think that I moved around a lot in my life, but Anja definitely beats me, having lived in 8 different countries and traveled to about 30 in total. Like many here at the HPL, she's very much into biking, but not in the same way that you or I think about biking. So she says that she really likes doing stuff like handstands on the handlebars or pulling wheelies, and apparently it's an entire sport called artistic cycling. And I take her word for it because Anja actually coached in that sport for 5 years with the Bavarian Sport Federation. So,
prove it.
Give me a bike.
Yeah. One of these days, I think we need to do an HPL talent show.
A talent show, uh-oh.
Yeah. But so with all that in mind, I'm going to drop the mic here, pass it on to you for your talk.
Thank you. If you want to build a skyscraper, you can reinforce it at the top to make it as high as possible and as stable as possible. You can reinforce it at the middle section or at the very bottom. If you're smart, you reinforce it all the way from the bottom to the top. But if you forget about the bottom part here, the entire structure will be weak, unstable. Worst case scenario, it's going to collapse. We can use this analogy for the human body as well. So we can think about it that way. We can work on our shoulders, hip, spine, knees, and our feet to make the entire body stable and strong. However, if we forget about the feet down here, the entire body will be weak and might be even unstable. Therefore, we need a strong foundation to provide stability all the way up the kinematic chain. If you think about it a different way, if you start limping and you limp for a long time, you will soon have issues in your knee, your hip, and your spine. So if we do not understand foot movement and what causes problems in foot movement, we won't be able to fix those problems. If you start Googling foot movement, very soon you will be confronted with one word: pronation. Pronation is defined as the inwards rotation of the foot about the subtalar joint axis. The subtalar joint axis is indicated here as a yellow line running through the talus bone. You can see the talus bone here in the middle, between the rear foot, the tibia, and here on the side you still see the midfoot bones. As you can see, pronation is a highly complex movement. Assessing pronation non-invasively directly at the talus is almost impossible. Therefore, it's not surprising that a lot of researchers try different variables that might or might not assess pronation and try to approximate this movement of pronation. The reason why pronation gained so much attention in literature is mainly because it was linked to injuries at some point. A lot of research was done in linking pronation injuries or pronation and overuse injuries, such as medial tibial stress syndrome, patellar tendinopathy, patellofemoral pain, non-specific injuries targeting the ankle or the foot, or even stress responses targeting the bone. Most of those studies, however, claim that if you minimize pronation, you will reduce the risk of getting injured. And also, most of those studies, as every other study, has the limitations. So if I just pick those studies I cited here and we look into sample size, study design, as well as what variables they were looking into, we end up with a table like this. So we have our 5 studies in the rows, and we see that most of them have a cross-sectional study design comparing injured participants and healthy participants. Therefore, what they're not able to do is to say whether the injury came because of a pronated foot posture or the pronated foot posture came after the injury. If you look into the sample size of those studies, you also see that most of them have less than 30 participants per group, therefore relatively small. And again, if you look into the pronation variables they use to quantify foot posture or foot movement, you can see that all of them use different variables. One of the studies I cited is just one example of what can also be done. It's a longitudinal study design. In this case, the sample size was a little bit bigger, with just over 100 people, but they only recruited military recruits. And as we know, military recruits is a very special population. They have specific boots they wear the entire day. So whether the findings of this study are translatable to a normal average population is questionable. However, all of those studies claim that pronation has a link to lower extremity injuries. In contrast to these findings, there is one study that definitely stuck out. That's the Nielsen Study, published a few years ago. They assessed almost 2,000 feet over the course of one entire year. They grouped those 2,000 feet in 5 different groups using the foot posture index. The foot posture index is usually a clinical tool that is used from physiotherapists a lot, also more and more from biomechanists, to predetermine groups of specific foot posture. Consists of a variety of different submeasurements and is combined in a total overall score. And that resulted in those groups from highly supinated foot posture over neutral to a highly pronated foot posture. As I mentioned, they monitored their participants over the course of 1 year and reported the incidence rate per 1,000 kilometers. And the most exciting news that was found in that paper is if you look into the pronated group. As you can see, this is the only group that reported a significant decrease of incidence rate per 1,000 kilometers. Therefore, the researchers concluded that pronation might be even an advantage compared to a neutral or even supinated foot. However, you can argue, well, what about the highly pronated group? There's a drastic increase in incidence rate per 1,000 kilometers. Well, if you look at that, the first thing you mention or you will see is the big spread in the data that makes it non-significant in the first place. And secondly, if you look into the sample or the group size, you see that this is less than 1% of the overall sample. It is questionable whether this 1% actually reflects the actual population outside of the laboratory that they looked into. If you ask a salesperson at SportCheck, for example, and they let you run on a treadmill and tell you whether you're a pronator or not a pronator, probably about 50% are all of a sudden pronators. And here we have less than 1%. Physiotherapists and clinicians usually range somewhere in the middle between those 1% and 50. But again, less than 1% is a result that is, at least we have to think about that critically. However, the overall conclusion of that paper was that pronation is not a risk of injuries. It doesn't increase it. Now we have 2 options. Does pronation increase the risk of getting injured? Does it not? Is there a link in between? I already mentioned it, that pronation can be assessed with a variety of different variables. So we took one step back and had a look into literature what was actually done, what variables were used to assess pronation. I grouped them here for simplicity into 6 different categories. So what we have on the top left is the longitudinal arch angle, which is an angle going from the base of the first metatarsal to the navicular tuberosity to the medial malleolus. We also have the rear foot angle, which is a typical biomechanics variable that describes the frontal plane movement of the rear foot relative to the floor. We have the arch index. It's usually assessed via plantar pressure measurements that describes the midfoot area relative to the fore and rear foot area. The Achilles tendon angle, the frontal movement of the rear foot relative to the frontal movement of the shank. We also have a category called navicular tuberosity that includes any measurements that target specifically the navicular tuberosity, such as navicular height or navicular displacement in the vertical or medial lateral direction, and the foot posture index that we already heard about. Not only do we have a variety of different variables, but you can also assess them in different static positions or in dynamic. In total, we counted 27 static variables and 34 dynamic variables. The reason why we ended up with so many different static options is, for example, that you can assess the longitudinal arch angle in bipedal standing, in single leg standing, etc. Therefore, we included these as independent variables. From there, we had the following research questions. The first question was, can we simplify our data collection? Can we make assumptions about the dynamic foot movement by just assessing static foot posture? The second question was, are there independent groups within the data set? The idea was all of the variables claim to quantify pronation, so they should all measure the same movement. There should not be independent groups. And the third question was about the foot posture index, since that is one of the measurements that is frequently used, that is very popular, and gains more and more popularity also in the field of biomechanics. So how important is that in our entire data set? And in the end, I would like to talk about the next steps, what we learned from our research that we did so far and where we want to go from there. So I will start with a comparison between static and dynamic variables. We collected 40 participants, 26 males, 14 females, in 4 different static positions. The first one is the typical bipedal upright standing, but we usually have in a biomechanical setting. There's also a position called subtalus neutral standing. Therefore, we palpated the talus. You can palpate the head of the talus if you touch the front on the dorsum of the foot, and you can instruct your subject to roll the ankle inwards and outwards until you feel the talus head equally prominent on either side. That would be the talus neutral position. We also collected single leg standing with 20-degree knee flexion and 30-degree knee flexion. This reflects the mid-stance average knee flexion angle during walking and running respectively. We obviously also collected walking and running trials at a fixed speed, and we averaged our results over 3 static trials and 5 dynamic trials. The entire data collection was done barefoot, simply that we can apply all the markers at the actual anatomical landmarks. So the result to compare static versus dynamic variables is as followed. We performed more than 900 Spearman correlations. That's a tremendous number of correlations we did. And first I want to summarize big picture what we found. 3.6% of the correlations were significant and strong in their magnitude. So a really, really small percentage. Just about less than 11% were significant but moderate in their magnitude. And the majority of correlations were not significant and if at all weak in their magnitude. If we looked further into where the correlations occur, we've seen that 4 out of the 6 categories actually reported correlations. Only 2 out of the 6, namely the rear foot angle and the foot posture index, did not show any correlations between a static assessment and any of the other dynamic variables. It was very surprising for the rear foot angle, since that one was collected in static as well as in dynamic, and there was no correlation even within the category itself. It was less surprising for the foot posture index, since the foot posture index only consists of static variables. Therefore, it was to be expected, at least, that the translation to a dynamic foot movement might be limited. One comment I want to make is that the internal correlations, so within one category, were always very strong. We had no strong correlations across categories. What I mean with that is that an internal correlation would be, for example, a static bipedal longitudinal arch angle that was strongly correlated to a dynamic measurement of the same variable. We had moderate correlations also across categories. So in summary, that means that only for specific categories, and within that one category, we can make some assumptions and approximations between static and dynamic. So we can simplify there. It is not possible across categories, or not recommended, and for sure for the rear foot as well as for the foot posture index, more than questionable. Which led us to the second research question we had. So the initial idea was, we do not have independent groups. Everything quantifies one movement, and that is pronation. The correlations, however, already showed us that there might be some of the variables that quantify something different, or at least are not correlated with other variables. So the question is now, do we have independent groups of variables within that data set of more than 60 variables? To answer that question, we performed a principal component analysis. I will quickly explain what a principal component analysis is in a very simple example. So if you think about the data, that looks like this. We have red and blue data points. And we run a principal component analysis on that kind of data set. We will get a first principal component along the axis of the greatest variance, principal component number 1. And we will get a second principal component along the axis of the second greatest variance, principal component number 2. The important thing is that those two components are orthogonal to each other and therefore independent from one another. They do not explain the same, or they don't contain the same information. This is per definition what a principal component analysis entails. In our data set, we had more than just 2 dimensions, therefore I will spare you the scatter plot with a multi-dimensional space, but nevertheless, a principal component analysis still led to a result. So we also contained 2 principal components in our data set. Only 2 because every principal component afterwards contributed less than 10% to the total variance. Therefore, we only chose the 2 most dominant ones. The first one explaining a little bit more than 30% of the total variance and had 10 dominant variables that contributed the most within that component. 4 were static variables, 6 were dynamic variables, but all of them belong to the longitudinal arch angle. Similar was the second principal component, just that all the 10 variables, 4 in static, 6 in dynamic again, belong to the Achilles tendon angle. That means, per definition again, both components are independent from one another, and therefore they contain different information. Consequently, if we measure midfoot movement using the longitudinal arch angle, it does not contain the same information as ankle joint movement measured by the Achilles tendon angle. Therefore, those 2 variables describe 2 independent movements. What we have realized, though, is the foot posture index was not part of the correlations, nor of the principal component analysis. It did not show up in any of our analysis tools. So the question is, how important is it? It is still very frequently used. So what we did was we repeated the analysis just with a reduced data set, simply because the foot posture index in the first data set was 1 variable, 1 overall score combining multiple step measurements. Comparing that to more than 60 variables might be a little bit unfair. So we thought, well, we cut the foot posture some slack, we give them an advantage, and we reduce the data set. So what we did was we used all 6 sub-measurements of the foot posture index and included the total overall score. So we had 7 static measurements of the foot posture index. And we also included the rear foot angle, Achilles tendon angle, and longitudinal arch angle again. The latter two because they were the most prominent factors of the first analysis we did. The rear foot angle was included because one of the sub-measurements of the foot posture index is almost the equivalent of the actual rear foot angle. And we expected that we at least see some correlations there. This time we included only one static measurement per biomechanics variable, which was the bipedal upright standing posture for this variable. Since the foot posture index is collected in upright standing, we thought this might yield the best result for any correlations afterwards. And again, we ran correlations as well as a principal component analysis. The result of the correlations gave us just 5 significant correlations. They were all targeting the medial longitudinal arch congruence, which is one sub-measurement of the foot posture index. And that sub-measurement was moderately but significantly correlated to 5 measurements of the longitudinal arch angle, 1 in static and 4 in dynamic. Surprisingly again, the rear foot angle, which we hoped for to show us a correlation, was not part of the results either. So whatever the rear foot used with the foot posture index or assessed with the foot posture index measures, it's not the same as the rear foot angle that we use in a biomechanical setting. And the results of the PCA further supported the lack of connection between the foot posture index and the biomechanical variables by yielding a similar result as the first analysis. Again, we only had 2 principal components that explained more than 10% of the variance each. This time, both of them explained more than 85%, so that's an increase compared to the first analysis. But both of them already, the first one consisted of the longitudinal arch angle again, the second one of the Achilles tendon angle. So nothing changed there. And it wasn't necessarily a surprise that those two dominate even the reduced data set, since they already dominated the larger data set. The surprise again was that no foot posture sub-measurement was part of the principal component analysis to a very dominating degree. In summary, for the foot posture index, that means in our data set, only one sub-measurement targeting the medial longitudinal arch can be used for any approximations of the longitudinal arch angle in a dynamic setting or static. All the other sub-measurements seem to have nothing to do with the, I call them typically used pronation variables, and therefore especially the foot posture index is not suited for a dynamic setting or for make assumptions about dynamic foot movement. Even though it is quite frequently used to pre-group those participants with the foot posture index to then assess foot movement. So what do the results mean for us as biomechanists, and how do we deal with them, and how do we incorporate them in future studies? The first thing we would like to suggest is, instead of saying we are doing research in the field of pronation, we are actually not able to quantify pronation. We don't even know which of the variables quantifies pronation. We should rather call it we do research in foot movement, therefore, to avoid this miscommunication that we actually measure pronation. We should also focus on the entire foot. Typical research, especially on pronation or foot movement, mainly focuses on the rear foot, but the entire foot is important. And I want to make a strong case why that is. If we look into movement transfer, we know that the rear foot is strongly connected to the tibia. So if you look at the picture on the right and you look at the blue arrows, if we have the heel everting, we know that the tibia is internally rotating. The opposite happens if the calcaneus is inverting, the purple arrow at the heel. The tibia or the shank is externally rotating. We know that this kind of movement transfer is happening. And the idea is that that is also happening within the foot. And a lot of research was done in the past 20 years to show that it is happening between forefoot, rear foot, and tibia. I want to show you how that looks like and why that might be a problem for us, that we need to understand why people move that way and why we need to focus on the entire foot. We have here two participants. Subject 1 on the left in blue, subject 2 on the right in green. What we see here is the calcaneus inversion and eversion as a function of stance phase. We have 30 steps, and the average is in a black bold line in the middle of those 30 steps somewhere. It was barefoot running. Both participants are running at the same speed. What we see that the calcaneus movement is almost equivalent. It has the same excursion curve, and it follows the same pattern. So we start at heel strike with an inversion until we reach maximum eversion, and then we invert again towards toe off. Knowing that the calcaneus is coupled or transfers movement to the tibia, we expect that the tibia follows as for subject 1. So for as long as we evert, the tibia internally rotates. And as soon as we start inverting, the tibia externally rotates towards toe off. If this had been the only input for tibia rotation, you would expect that the second participant, the tibia rotation looks the exact same way as the first one. However, it does not. So what that participant does is, in the first half of stance, something completely different than what you would expect in subject 1, and at the end of stance phase, something similar. The only thing that remains the same is the local maximum of tibia internal rotation that happens about the same time as the calcaneus eversion maximum. Therefore, we expect that there might be other inputs that are also responsible for tibia rotation. And we do know that the tibia is connected to the midfoot and the forefoot, as well as to the thigh, via passive or active structures. So what we suggest for future projects is to look into the effect of the entire foot on foot coupling, and to determine the effect of ligaments and muscles on coupling within the foot, as well as on the shank. We also want to investigate coupling between foot bones as well as foot segments. I will explain the difference in a bit. To target the first purpose, we would like to use something called the dynamic gait replicator to determine the effect of muscles and ligaments on foot coupling. We do not have such a device here in the HPL, so we will collaborate with the Iowa State University and Dr. Tim Derrick, who was Dr. Brent Edwards' PhD supervisor, and Dr. Aaron Ward. They have this device there, and they used it in the past already, so we know it's working. What we will do is we will mount a cadaveric foot onto the tibia rod, connect 8 muscle tendon units to a cable that is again connected to a motor, and that motor can exert forces onto the muscle tendon units, and therefore makes the cadaveric foot walk. The nice thing about cadaveric studies is that you can manipulate whatever you want. So we can manipulate the muscles and how much the muscles are loaded. And therefore, we can mimic muscle weaknesses. We can also bisect ligaments, which we cannot do in vivo subjects, I guess. Therefore, we can quantify the effect of ligaments on coupling behavior in a semi-dynamic setting. But we don't only want to do an in vitro study. We also want to do an in vivo study to determine coupling between foot bones. And there are 2 options how we can determine bone coupling or bone kinematics. You can either use bone pins or medical imaging. We assume that if we go for the bone pins, we will have a hard time finding volunteers, so we opted for the medical imaging. Therefore, we need 2 medical imaging modalities. First, a computer tomography scan. This will enable us to get a 3D model of our body of interest or bone of interest. So in this case, we have a scan of the ankle. We can determine which bone you want to have. And in this example, we ended up with a calcaneus bone. We also need something called dual fluoroscopy or biplanar X-ray. What the name already says is we have 2 X-ray sources that are imaging at the same time through our foot and result in an X-ray image on 2 intensifiers, image intensifiers. And the high-speed cameras behind the image intensifiers are recording those images. So instead of just getting one X-ray, what you would usually get if you break your ankle, for example, or your arm, you will get a series of X-ray images. And it looks like a video sequence later on. What we will do then is we put this 3D model of our bone into a virtual lab, where also our 2 planar images of the X-ray are. And we rotate this bone model for a certain amount of time until it matches almost identically those images of the biplanar X-ray. And we do this for every single frame consecutively. So what we'll get in the end is the actual bone movement. And we can repeat that not only for the calcaneus, but for every bone we're interested in. Next to bone coupling, we can also do segmental coupling. Segment coupling is the only difference that we combine multiple bones into one segment. As biomechanists, we usually use motion capture, and we assume that we have a rigid body consisting of multiple bones, and there is no motion between those bones within a segment. We do not know if that is actually true. We simply assume this is how it is. We want to compare whether this holds true for coupling. Therefore, we would include motion capture on top of the dual fluoroscopy study to be able to make assumptions about how far we are off with a motion capture system if we want to quantify segmental coupling. Since we also do not have a dual fluoroscopy system or a CT scan here in the lab, we will do that at FootLoose Hospital in collaboration with Dr. Janet Ronsky and Dr. Gregor Kunze. And I'm happy to show you some of my pilot data just obtained 2 weeks ago from the dual fluoroscopy image. I assume most of you have never seen dynamic X-ray images. So what you see here are the 2 images from the image intensifiers we obtained. This is raw data, it's not filtered, it's not edited, and we just see a walking step of one participant, it's the same step, and I just replayed 3 times so you have some time to look into the different bones. On the left side, you see the perspective from a superior and lateral view through the foot. From the right side, you see a superior and medial perspective going through the foot. And what you see are the midfoot bones, the metatarsals, the rear foot, as well as the distal end of the tibia, coming into the field of view and going out of the field of view again. What we expect to find with those 2 proposals of the next projects is, first of all, that we're able to describe and explain coupling between bones within the foot and up to the shank. And that we're also able to describe where are the differences between bone coupling assessed with medical imaging devices and motion capture, and where are the limitations that we have to work with. As well as the in vitro study, we hope to quantify the effect of muscles and ligaments on coupling. Finally, I would like to end with a quote from famous Isaac Newton. What we know is a drop, what we don't know is an ocean. So we do know quite a bit about foot movement so far, but we definitely do not understand enough to make sure that we know where are injuries coming from, how do we deal with them, or how do we improve performance. So with the studies we suggest, we hope to understand foot movement better and in more detail. And with that, I would like to thank my committee members, my supervisor and co-supervisor, as well as my collaboration partners. Thank you.
Awesome. I'll open the floor to questions.
That is tame indeed. I was warned.
Yeah, come on.
So you had something as, it was one of your expected findings, or speculate, but when I saw those two graphs of the people walking.
Yeah.
Yeah, so do you think those differences are mainly due to muscle, or do you think it's more due to like ligaments, or so do they have like different walking strategies, do you think? They're just activating their muscles differently, or they actually have like a physically like tighter ligaments holding their foot together?
I have no idea why we've seen that. I would purely speculate here. Since we did not collect EMG, so I cannot make any assumption about whether the muscle was more active, less active, what they did. I asked whether they had injuries or something regarding the ankle joint or lower extremities. All of them said no. However, maybe there is something in there the person doesn't know about. I wouldn't know about it either, but I have no idea why we see that pattern. The idea was that maybe the forefoot, the midfoot, or the thigh give a different input into the tibia, and that is why we see something like this. However, was very unexpected to see a shape like that, and we cannot explain why that is right now.
So in the beginning you mentioned a couple of studies.
Yeah.
So it seems that there is in the literature, there's been made a relationship between this pronation and injury. Is there also a theory about how this comes about?
It depends.
So why this relationship is there, or is it only a correlation and no causality?
That's the problem if you have a cross-sectional study design, that you can't answer the causality question. That was the first problem. A few people only put their actual time and work into a longitudinal study to try to find something. However, since everyone is using different variables, you can't really compare cross studies. That is different. And everyone looked into different injuries as well. So whatever might be true for an Achilles tendinopathy or Achilles injury might not be true for bone response. So it feels a lot like everyone is doing something, but the bigger picture is a little bit missing.
Okay. And do you have an idea about how more or less pronation could lead to injuries?
Pronunciation. I have the same problem sometimes.
Pronouncing it might be weird.
I understand if people try to link it to knee injuries. If we see here that the rear foot is linked to the tibia, and therefore a pronation movement, if we say pronation is the same as rear foot eversion, that could lead to more internal tibia rotation and therefore create some problems at the knee. I could see that argumentation. I'm not familiar with how injury pathologies and how that develops, so I'm not 100% certain about the other injuries, if that has actually a reason for it, but I'm very certain since so many people researched that, there probably is a reason for it, why.
I see. Okay.
On that point, by the way, I'd like to encourage the group to kind of jump in, and if you have something to add, like treat it as a discussion, not just question and answer. On that point, we recently did a study where we had one person, Olivia, on the treadmill, and we got her to walk with a very exaggerated type of footfall. I'm not going to call it pronation because you just told me I shouldn't. But when she exaggerated the way she lands her foot, it changed the free moment, and in my finite element models, it changed the amount of torsional deformation on the bone. So it's only one person, it's only a very limited set, but I agree with you. I kind of see why there might be that link between what you do with your foot and ultimately what the tissues feel. So yeah,
that's cool.
So I'll follow you up by saying I'm not sure. Despite the fact that I'm an author on that paper, I'm not sure that I fully believe that the movement that the gross exaggeration that Olivia did represents a relevant movement in terms of. But I still would say that there's probably something there. But also on the second part, that it's probably more important in walking than it is in running, right? Given that.
I'll trust you on that. Yeah, sure.
Well, no, it was kind of this that it was mostly in the torsion aspect, right? So when you had the torsion, whatever, exaggerated the amount of, I can't remember how we had you walking more.
Yeah, it was, I think I was trying to rotate my foot while it was on the ground.
It was basically exaggerated to create a larger free moment.
Yeah.
It seemed.
Yeah.
The push off is definitely trying to put the heel out.
Yeah. I guess I just don't know if that.
Of course, because we were trying to get her to do something weird and not
natural. It was very awkward.
On that note, not to take away from Anja's talk.
All good.
Art?
I'm curious about the relationship between the physical components you found and the previous literature where people said, high pronation. So do you think that that high pronation just means nothing and that it's just, in terms of physical components, it's just all sorts of different patterns? Or is there anything where high pronation corresponds to a particular combination of them?
The first thing, I think high pronation can cause problems, yes, if we would be able to actually measure pronation as a talus rotation. With those variables we have at the moment, the approximations and estimations of pronation, I guess, include. I don't know if the principal components we have, the two dominant ones, the long-term arch angle and the Achilles tendon angle, were used in literature quite extensively in terms of creating or trying to find a link to injuries. If that is what you're going at, I'm not quite certain with the principal components what you meant by whether they...
Well, I just mean that in previous literature, when they said high pronation, they must have meant something. And then, well, or I'm assuming they meant something. And then ideally, we would be able to describe that something in terms of principal component. It's 0.2 times principal component 1 plus 0.6 times component 2.
So I'm not aware of anyone who actually came up with an equation for it, what pronation is, and when someone is pronating more or less. That would be very interesting to see if you can actually combine multiple factors and weigh them differently to come up with something that measures pronation. From the principal components itself, I don't know how you would know whether they actually are pronation or not. Every single variable we chose was in the literature somewhat related to pronation in the past already. So the idea was they do quantify pronation. It was surprising to find that they were split up in actual categories, and therefore the problem was more like for us, so which one now is pronation and which one is not? And we cannot answer that with the study setup we have. So I would purely speculate here. I would have no idea which one actually describes pronation, or if a combination of multiple principal components does describe pronation. Couldn't say it.
Right.
I just want to seek some clarification from you. Do you define pronation the way a clinician would? Dorsiflexion, it's a combination of
dorsiflexion, forefoot abduction, and rear foot eversion.
Yeah.
The way we would define it usually is the rotation of the talus. So the inwards rotation. So if you think about, if you remember the first video I had in there, this one, does it play it? No.
How did they make this? Did they use dual fluoroscope?
I have no idea. I found it online. So if we look into the rotation around this axis, that would be the actual definition of pronation. But also this axis moves as well.
Yeah.
So I think that is why in a clinical setting and also in a biomechanical setting, we try to split up that movement into different components and see whether we can quantify the different components. And that might then lead back to what Art was asking. Maybe there is a way to combine different components to get the actual measurement of the rotation of the talus. It was never done before.
Yeah, we can follow up.
You end up with is PC1 and PC2, and PC1 is related to the longitudinal
arch angle, yeah.
And the other one's related to the Achilles tendon angle.
Yeah.
How do you relate those PCs back to those two variables? Is that...
If you run a principal component analysis, you get your eigenvalues. And they correspond to every single variable I put in. So I know which variable contributes more within each principal component than another one.
So then it was basically all of the longitudinal arch measurements that were...
Yeah, so what I can show you what I did is, this is for the first example. So we have our 60 variables, a little bit more than 60 on the x-axis. On the y-axis, our eigenvectors, sorry, not eigenvalues. Within principal component 1 and 2, respectively. And I know the order. I know which variable is variable 1 and which one is variable 60 something. And I know how much every single variable contributes to this principal component. And we said everything, we always have this gap in between about 0.2, where we see this is all of a sudden we have a few variables above, and then it makes a jump, and all the other variables are below this threshold. And this is how we determine their dominant variables, how we called them, and all of them seem to be within the longitudinal arch angle for PC1 and the Achilles tendon angle for PC2.
Okay, and then because they're orthogonal to
Yeah.
one another, can I interpret that as meaning there's no correlation between longitudinal arch deformation and Achilles
Exactly.
tendon angle?
Yeah. Zero correlations. Yeah.
Eric, you had a question?
So basically you showed that the foot posture index is more related to the longitudinal arch angle.
One of the sub-measurements of the foot posture index.
So what are the other measurements of the foot posture index?
We have a forefoot measurement, a rear foot measurement, a navicular measurement, if I remember correctly, the arch congruence, something that is called, it looks into how bulky the area underneath your ankles is. I assume it relates to something like a trauma at some point. I don't know by heart anymore, but there are 6 different sub-measurements going through the entire foot, basically, including forefoot, midfoot, rear foot measurements. The difference with the foot posture index is you score it subjectively. That's why we practiced with a physiotherapist and went through a number of feet first to be able to see like whether I'm reliable or not.
Yeah, Andy, and then Art.
Just following on from that, I was
Yeah.
wondering about the importance of reliability in your correlation analysis, and if there's any links between how reliable these 60 measures are and how
Yeah.
correlated they are with each other in
Yeah.
symmetry analysis.
So we didn't do a reliability analysis on the actual biomechanical variables. That was already done way before because they have been used extensively in literature. So they are validation as well as reliability studies out there for I think all of them but one that was published when I published also mine I've seen now. So they seem to be very reliable, inter-rater as well as intra-rater reliability. The foot posture index, you find publications across the whole spectrum. Some people say not reliable at all. Some people do say very reliable, depending on how well trained the person is. That's why we chose that I practice first with the help of a physiotherapist. I think we had 30 to 40 feet, multiple days, multiple times, also within the same day, to make sure that I can actually score objectively. Yeah.
Art next. Yeah.
I just want to make a slight modification to the discussion you just
Yeah.
had with Brent about these 2 variables.
Yeah.
And I think I wouldn't quite say that there's no correlation between the variables. I think the interpretation of principal components is they are by definition 2 coordinates that you could explain your data in, and they can explain a lot of the data.
Yeah.
But each of those components will have, like one of them has more longitudinal arch index and the other has more Achilles tendon angle. But in general, any movement is some combination of these.
Yeah.
It's not like they're uncorrelated. In general, they have some correlation. And then even in each component, both of them can appear. It's just that they appear in very different ways.
Exactly, that's what I wanted to show with this picture here, that we see that whenever, let's say the first few are the longitudinal arch angle for PC1, they still contribute to the second one as well, just not as drastically as towards the first principal component. However, when we checked for correlations between the Achilles tendon angle variables and the longitudinal arch angle variables, they were not significant and only weak in their magnitude.
Sure. Michael?
Anja, at the beginning, you mentioned the first slide was all about, you don't need to go back to it.
Yeah.
You know, you talked about, if you wanted to build a strong structure, you should build it, strong at the foot. But then you mentioned strength there, and then never again. So
Mhm.
A, why did you lead with strength? of the structure if you didn't follow up with anything about strength? And then I guess that follows on to, do you think that strength actually matters in how people live?
I think what I wanted to emphasize with the skyscraper analogy is that we care about the strength, yes. We need a strong foundation, but if we don't know what's happening in a dynamic scenario, how can we even deal with strength and think about how to make it stronger and more stable if we don't understand what is going on from a foot movement perspective? And yes, I do think strength matters, but I never did any coaching in foot strength measurements or anything, so I wouldn't know where to start there. However, I think it might plays a role in terms of if you're injured and you want to get back on track, that you have to do some physiotherapy that includes strengthening protocols, which is, I think, probably the norm, what people go with. But it is more the reason for why we need to understand foot movement. If we understand that, we can also build the protocol for strengthening or look into the effect of strengthening protocols in more detail and see the effects there.
That's something to understand the problem with the foot posture index. Is it that it was not validated properly to actually quantify pronation, or it's quantifying some aspect of pronation that is not important to injury? What's the problem with this measure?
The foot posture index?
Yes.
So it was developed with or validated with different variables. And again, since some people report, yes, there is a relationship between foot posture index and a specific variable, other people say, no, there is not. And they always have different populations, different raters, sometimes experienced, sometimes not, that comes into play. So we don't know if we just look at literature, if the problem is the measurement itself or how people use it sometimes. However, the way they set up the measurement, they wanted to have a measurement especially for the applied population that uses a quick measurement, the foot posture it takes, if you're skilled, 5 minutes to assess and to take the overall foot into account. If you want to do a biomechanical assessment, you need motion capture analysis, etc., etc., etc. For most physicians or podiatrists, that's not a common practice. So that was the origin where it came from, why they developed that. There is a validation study out there as well as a reliability study, and for the variables they choose, it was valid. However, most people take that out of context and use it simply to pre-group the participants they have and then say, everyone with that foot posture does A, everyone with the other foot posture does B, which was not the original plan for the foot posture index necessarily. So I think that was the major problem.
What's the foot posture index give you at the end of the day? You do these measures, is it some number?
It's a score, yeah, from -12 to +12. And
so,
then there are norm
an
values.
Thing, or can you have 12 and a half?
Ordinal, yeah. So what after they came up with a score, they also had a study about what are the norm values, where people usually fall into, what kind of bins. And most people are slightly pronated, so it's not 0 is the norm, perfectly neutral, but everything is shifted a little bit towards a pronated foot posture. But they use exactly that term again, which also makes it difficult.
And so these studies that use it when they're grouping people by these
beforehand,
bins,
yeah,
those numbers are defined.
Exactly, yeah.
Just to follow up on that. So then if they use anyone with a score below 0 as pronated when everyone is, say, like a -1, that they should just shift the cutoff and then they might get
So
better.
before the norm study, they just said 0 is neutral, whatever goes into a plus minus, and I think +2, -2 was still considered to be neutral. Then it depends on the paper you look into. Some people only grouped into pronated, neutral, and supinated, and some people, as the Nielsen study did, they did this moderate group in between as well. And some of them in the beginning just chose, there is a scale coming with the actual manual saying everyone who falls into this category is supinated, pronated, and so on. And after this normative value study, everything gets shifted a little bit more towards the pronation direction, and that seems to be the norm. And the average healthy person has a slightly pronated posture according to the foot posture index.
Any more questions? Nope.
Michael.
Yeah, go for it.
Sure. Okay, so we can go back to strength again.
Yes.
I like this.
Great.
My first comment is that I would be very wary of going down the path of trying to link strength and kinematics in healthy individuals. The primary reason is that a whole lot of people spent the last 20 years trying to do this at every other joint with zero success, right?
Yeah.
The only thing that strength is being linked to is no change. Like, you can strengthen all you want, you can never change movement patterns. The only thing that strength does is help to reduce people with pain. Helps with people who have patellofemoral pain to get strong. So I found this occurs often when people, like, the foot became very popular and people all of a sudden again said, wow, strength really matters a whole lot. But like, why would people think that strength matters at the foot when it plays no role in any other joint? It's just an erroneous kind of road to be going down when we already know that it doesn't matter in any other place. But the backside to that is that strength obviously matters, like in a rehabilitation setting. And in like the extreme scenarios, like if you fracture your ankle or something, then you obviously have weak calves, and that might be an interesting road to go down. Like, I thought this after breaking my ankle, that probably would be really interesting to look at, because you have weak calves,
no calves,
I couldn't push off very long. And what ended up happening was I had a ton of pain in the midfoot, because it seemed as if I was compensating there. But no one has studied this, at any point. There doesn't seem to be any research in investigating how kind of foot function changes after prolonged kind of like cast wearing and mobilization, and then what the effect of is like those reduced muscle functions on the thing. And maybe your cadaveric study could answer that, which would be interesting.
It could definitely answer like ligament ruptures that we could mimic with that. Also muscle weaknesses, as we already talked about. However, I would argue with strength, we might not be able to change the movement pattern, but we might be able to change the variability within the movement. I know that some people did that regarding the foot, especially when it comes to coupling, and looked into coupling variability. And it seemed to be that injured people, some claim you have more variability because you have more like a loose, uncontrolled setting. Other people say if you strengthen, though, you determine again your path of motion, and therefore you might see an effect there. I have never done it. I don't know the literature behind it too well. Yeah.
I know you had a question.
I think strength matters, especially for the small one. If you take the foot and you take the 11 muscles, tendon units that you have, and you take all of them away except the tibialis anterior and the triceps superior, and you try to balance yourself, you probably have loading that is asymmetrical with respect to the Achilles tendon. That is usually the origin for injuries. If you strengthen bones, then they take over some of that balancing. You unload the bigger muscles. So you probably will not change the movement, and you will change the way how the different muscles contribute the stability in gait. That is very important.
I could believe that, but I don't know if arguing from the perspective of taking out all of the muscles is a good way to start. Because I agree, if you remove the muscles and you just have two, then the stability is probably compromised, simply because you're talking two muscles that largely act to dorsiflex and plantar flex the foot, whereas the intrinsic kind of foot muscles like the flexor digitorum longus and posterior tibialis have more contributions to frontal plane and transverse plane motion. But I guess what I'm trying to get at is that small deviations in strength that you see with strengthening programs. I'm not sure would have a large effect even on the loading that occurs within kind of musculoskeletal structures.
I would disagree. And I would say that what changes dramatically, and you know, if I say dramatically, something like 100%, is the joint forces and the insertion forces. They change dramatically. If you have strong weak muscles, or strong small muscles, or if you don't have strong small muscles.
Yes, I don't.
I have some anecdotal evidence. I don't have the evidence yet for an experimental evidence.
I mean, I guess it's difficult to tease out what would happen. I suppose that the only way to answer the question is to do an invasive protocol involving lots of indwelling EMG and dual fluoroscopy or something.
No, I mean, if you measure the EMG for people that have strong older fixed direction, then that looks completely different than the EMG for people that have weak small muscles, weak ankle joint muscles.
Only the relative magnitude, probably, but the forces that are acting on the foot wouldn't be different than any other. So the total muscle force that needs the joint moment that needs to be replicated by the muscles.
No, but if you have to use triceps sura for stabilizing, then you have also to activate the tibialis posterior, and you have to activate the quadriceps and the hamstrings. So you increase the joint loading. So as a simple example, if you have knee pain, you can probably get rid of that knee pain in most cases by just strengthening small muscles of the ankle joint.
I'm not sure the research supports that statement, but I also am aware that there's not much research into that. The claim that you can reduce pain.
That would answer.
Yeah. Mostly people focus on strengthening in the quads to reduce knee pain, but the answer is why.
Brett, I'll switch gears here.
All right.
Do you think that there's merit in quantifying subtalar motion extremely accurately if you can only have somebody in a partial weight bearing or non-weight bearing scenario? Would that be at all relevant to the type of question that you want to answer?
I think if we can translate that to walking or running, that would help. But I wouldn't know how we can non-invasively quantify talus motion.
Well, I'm working with a group out in McKay, and they're more interested in sort of what happens with subtalar fusions and things like that. But we're now doing dynamic CT in the scanner, and the radiation dose is extremely low, but it's going to be three-dimensional, way more accurate than the dual fluoro will be, than any motion analysis thing will be. So I don't know, it's just something that I thought about.
No, it's absolutely interesting. Yeah. No, that's.
Oh, do we have someone for?
We got a question from Robert.
Okay.
Robert, you ready? Go ahead.
I'm ready, thanks, Howard. In your first slide, you talked about the stability of the body and strength of the body and the leg and then the feet. But there seemed to be another variable, and that's the surface of the ground. I know that my major injury occurred from traveling on a very unstable surface at a significant angle, and that if you were looking at foot conditions and foot mobility, most of what I think I'm seeing in your talk is based on a very flat and a stable surface. Have you looked at the possibility, if not an unstable surface, but looked at the possibility of a highly angled surface, and that's those limits of the range of the ankle are where injuries may occur.
So we haven't looked at an angled surface or an unstable surface. I know that there are researchers out there that try to quantify the range of motion of the ankle, or they call it the subtalar joint, and therefore quantify the boundaries of the movement. And then in a dynamic setting, they quantify how close you are to these boundaries. And if you want to believe them, they say the closer you are to your, in this case, passive range of motion boundaries, the more likely you are to get injured. So that could be something absolutely that could be looked into. And it might be a reason for why injuries occur. From my knowledge, that was done about 3 years ago and hasn't been picked up by a lot of other research groups. It mainly came out of this one lab, where I do not remember the name right now. So, but I assume that that could be a reason as well why injuries occur if you're too close to your actual movement boundaries, yes.
Thank you.
All right, Anja, I have a question for you.
Uh-oh.
Unfortunately, I have to go back to the strength topic.
Yeah.
But specifically, in relation to what Benno was saying, what do we know about how much force is actually being generated in those small muscles in relation to how much force they can generate? Because I would say that if they're only generating small amounts of force, then increasing their capacity probably wouldn't do anything, whereas if they're almost getting saturated, then maybe, yes, adding more force, more strength would do something more. So do we know something about these forces?
So I have no idea. I could only speculate that maybe small muscles, I'm sure they have a tremendous amount of force there. Otherwise, why would they be there if they don't contribute to anything? I could only speculate that it might have something to do also with the moment arm, the way you generate forces or moments that might be limited for the smaller muscles, but definitely Benno is the expert on that.
Basically,
for me, it's pure speculation.
Do we know if those muscles are getting saturated?
But earlier.
Sorry?
Very weak, but earlier. They act earlier. If you have to stabilize with the Achilles tendon, with triceps urae, till you feel that there is something that has to be stabilized, you are already way over. While the small muscles, you can sense that much earlier. So the point is they are active and important because they can react much faster.
Okay, I see what you mean. So if they're stronger, that means they could generate their forces even faster, basically. Is that the logic?
They need less force to act earlier than you need with the Achilles tendon, where you need the Achilles tendon is not made to stabilize with respect to subtalar joint action. But they have better levers with respect to subtalar joint action. Therefore, they feel changes earlier and need less force to react than the Achilles tendon would.
Okay, thank you. Any more questions? We have a little bit more time. Nope. On that note, please join me in thanking our speaker. So next week, for those of you who are here, we will be having